with rigid manifolds, projective classifying spaces, Inoue type varieties, and deformation to hypersurface motion. Right? So actually I'm very happy to be here, and because I'm one of the people in this room who are non-Russian who has met Fedia since long. So I remember we had the pleasure of meeting at this in 1977 when Fedia was giving these Gmail lectures on algebraic surfaces and lecturing about his results. At that time, he was already old because he was already probably 31, 30 or 31, maybe 30. He was not here. So for me, he was always senior. He was much older, but now with age. And I have to say that, you know, I can talk mathematics with him quite well, but I remember when he started his lecture, in Gmail lectures, he started to say something which was supposed to be English, but it was Gepa-ash. And then, fortunately, he wrote something like this, and some people understood. That G in algebra group, P parabolic, and H a Cartan subgroup, but not everybody. So anyhow, through the years, I remember we were 1 year in Princeton, and we discussed walking through the woods. We always discussed mathematics, and so in the end. Fedia has always a lot of questions, so I try to imitate him. You see that I also want like to pose questions, and of course my approach is always to look for examples, and I think his approach is no, don't look at examples because otherwise you don't see the general truth. So I think it's interesting that you can do mathematics in rather different ways. Okay. So. Now, okay, let me continue somehow. You see that Ingrid explained a theorem which, I mean, we've been working together. Actually, I've been trying always to avoid this proof. So, not that I didn't do my part, but at a certain point she obliged me to verify the proof, and which was rather painful. So we tried to explain why the theorem should have a simpler proof and why it should be more general, but unfortunately it doesn't really work. So this happens, it's quite common in mathematics. There are beautiful ideas, but then sometimes ideas which work not exactly the same, but it's still interesting. So what seems to me interesting about this thing is that it is like the tip of the iceberg, because now we have somehow, you take C is a configuration of lines in P. And then I H Hirzebruch covering of a configuration of exponent n means you're taking the nth root of all the linear forms. Okay, so this is the minimal resolution of x, where you just take Cin equal Lix. You're taking the nth root of all these linear forms. Now, it's rather clear that if you can move the configuration of lines, then essentially you move the surface. So it makes sense to consider that C is rigid. And in fact, it's one of the most classical theorems in algebraic geometry is that any configuration of type 9, 4, 12, 3, so 9 points such that through, and 12 lines, such that through each point they pass 4 lines, and each line contains 3 points, is projectively equivalent to the configuration of flexes and line through the flexes of a plane cubic form. Okay, this is a theorem which I teach, or I'm still allowed to teach in Bayreuth to the students for my teachers, and from which comes, is derived the Hesse normal form. Fermat plus lambda xyz is based on this. So this is projectively unique, as well as this complete quadrangle. Most people don't know geometry because they call it complete quadrilateral, but you see here are 4 points. And this is projectively unique, so also this iterated Brunel-Campedelli. This is something strange. Nobody realized in algebraic geometry that there exists this iterated.
It's also unique.
Pardon?
It's also projectively unique.
Yes, of course.
Because, okay.
4 points is projectively unique, so this is really, but it's interesting because it's, somehow it has some dynamics flavor, because you take this triangle and then you make it smaller and smaller and smaller, and yeah. So there are many rigid configurations. Now, you can ask some questions, maybe to save space. I will now go here. So there are these questions: when is S a projective classified space? Strong rigidity in the case of the complete quadrangle. And then more general, okay, there are some questions concerning rigidity. Can one find an infinitesimally rigid surface or general type which is not a projective classified space? So here, because I want to talk about too many things and maybe I don't make it, one example could be to have some surface, some hyperplane section, rigid, in a so if there's a remark that if S is a surface, is contained in Z, and I assume that C is a projective classified space, then there is a very easy remark, and S is ample, then S is not, let me write for short, is not a projective classifying space.
Yeah. Well, by one, yes.
Exactly. So should I, maybe for the younger people, I explain that by Lefschetz, the fundamental group of S is the fundamental group of Z. So if S were a projective classifying space, its cohomology would be the cohomology of this group. Now this is the cohomology of this group, and so H6 of pi 1 S Z is equal to Z. But if it's a surface, it's this would be H6 of SC, which is 0. Okay, so if you want something that is not a projective classifying space, just take a hyperplane section of a projective classifying space. So the hope we have is to find some Beauville manifold with a rigid. Okay, so this is like first candidate. So not only I want to put the question, but somehow explain why there is some hope.
But you can vary this hyperplane section.
Pardon?
You can vary this hyperplane section.
Yes, but it's ample, not variable.
But what about both portions in bigger dimension?
Pardon?
But what about both portions in bigger dimension? That's supposed to be rigid. By most.
A ball portion to bigger dimension. Yes. Z for Z.
It's rigid and its inverse covering is so it's projected to spline space. Give a sense?
Yeah, but I want something
Which is not.
which is not.
No, no, you mean despite S. That's the problem is despite
Which
S.
is not a projected classified
Yeah.
space.
No,
Then
he,
you
he
use
suggests the following.
Third.
Yeah, but, okay, yeah, I agree. So the main point is,
Yes.
I will talk at length about what we know about projected classified space. Now, the point is that we have found example of projected classified spaces with rigid divisors.
Yeah.
But in that case, S is rigid inside Z, but Z is not rigid. Okay, so, and again there we want the candidate, the canonical candidate would be a surface of general type where you contract the -2 curve and you get a canonical model which is rigid. But of course it's not infinitesimal rigid. Okay.
Fabrizio, sorry, maybe a stupid question. And is there a theorem that such a rigid surface of general type cannot be just simply connected?
No, no, no. No, they want even the less.
No, no, no. Of course that's, but there is no example. up
Yeah,
to
no,
now.
no, but it's still possible that you can actually have a simply connected rigid surface of
No,
general
you
type.
can, in principle, yes,
Yes,
why
in
not?
principle,
Yes, why not?
Why not?
So this is, so the question is just asking, yeah, okay.
Now, what I like about this topic is that there are a lot of interesting questions, and so what we can prove is rather little, but it's still not trivial.
It's still hard.
Yes, still hard. Yeah. So,
Normal surfaces and
okay, so I already explained that the first hint, a rigid ample divisor in a rigid threefold, which is again by 1, and then a minimal surface of general type whose canonical model is singular and rigid. So this concerns rigidity. Now, okay, so the general questions is really this one. If you take a rigid configuration of lines, then is it true that this surface is rigid for n large enough? In the case of the complete quadrangle, it was n at least 4. Actually, it's also interesting for n equal 2, this was very interesting in arithmetic, has been studied by Van Hemmen and Van Looy, and it's a very nice Katie surface. Because these coverings have this as S4 symmetry, S5 symmetry because of the del pezzo, then there has Z mod n to the 5. So there is the group of symmetries here is Z mod n to the R minus to the 5, and direct, semi-direct product with S5.
Yes, it's good.
And so this is interesting.
This is standard action.
Pardon?
This is standard action.
Yeah, this is the action on the del pezzo surface. I will explain this later.
This is a final step. I find it then.
No, it's not the standard action. I mean, yes.
It's a final step.
Yeah, I think so. Yeah, but it's not the standard one if you take about, you have to take a suitable basis. I mean, this is something concerning the geometry of the del pezzo surface that I don't think is the standard action. I should look at my notes because, pardon? No, because you see, this is just this is the cohomology.
Not much, not many possibilities.
You see, these curves here are indexed by doubles. They're not that standard representations. You see, the curves in the del pezzo surface. You have P1, so this is like P1 and this is P2. So this line here is the line E34. So this is really, it's not the standard representation. I mean, we can discuss it afterwards. I have my lecture, the Takagi lectures, I wrote something about this. And then, again, when is it a K-pi 1 for n bigger? So this is quite general question. And now, for the interesting question, also I've been trying for some time, if this surface would admit a Keller metric of negative sectional curvature or semi-negative, then by the Cartana-Hadamard theorem, the universal covering is contractible. So, and this is interesting because it also, with a certain stronger negativity, then you have strong rigidity by the theorem of CO. But this strong negativity of CO is difficult to achieve. So it's quite interesting. I've been trying to construct this smooth metric for these surfaces, but it's not so easy.
But these Panox metrics, they are smoother.
They're smoothable.
Yeah, so you can just try to do it.
You don't need smooth. The point is you don't need smoothness. You need negativity.
Yeah.
Just,
But why are they? Maybe that's interesting if you know why they're smoothable. Yeah, that's very interesting. Okay, I'm happy that we have something to discuss. And then, of course, état rigidity is also an interesting question. And then I say, okay, this was already said by Ingrid, there exists a smooth metric when phi divides n. Actually, was very interesting. I saw that there is this method by Siu of patching Bergman metrics together, and we wanted to do that with Alexander Vichy, but it turned out that it was already done by Fang and Tseng.
What is SM?
Pardon?
What is SM?
5 divided.
5 divides n.
What is SM?
Sn is the same thing as this for the complete quadrant. Okay, so now I can pass to the as the first thing to do to explain in a sense, we ask some question, it's not the time to make conjectures, but I want to explain why one can hope to prove results of this kind. Okay, so the first thing which I want to explain are what are these BCD surfaces. But before doing that, let me give a very simple theorem, which somehow was the origin of this question about rigidity. So assume that I have a surface as, say, minimal of general type. And the Albanese map has image so if the Albanese map has image and curve, assume that all fibers of alpha are smooth or have exactly one disconnecting node. Then they say,
What does the last thing mean? What does it mean to have a disconnect?
Non-splitting.
this means that there is a node, and when you remove the node, you get two connected components. So this means that there are two smooth curves
Yes.
intersecting transversally in one point. Then the same for all deformation. Okay, so let me give some idea. The main point is that, first of all, S prime, so here there is some arguments, they work also for, not only for deformations, but also for S prime homotopical equivalent. So, first point is that if S prime is homotopical equivalent to S, then H1 of S prime Q generates a subalgebra of H star S prime Q, which is 0 for degree bigger than 3. So H3 is subalgebra A such that AI is 0 for I at least 3. This implies that this implies that alpha prime from S prime against those two curves G prime and of the same genus. Now, the second point is that if S prime is diffeomorphic to S, then it follows by Seiberg-Witten invariance if G is the fiber of Albanese map, then G is equal to G prime. Because
Why do you mean Zyber? Is it not clear?
it's not clear.
So
Present day.
what do you mean by being equal?
Excuse me?
What do you mean by being equal?
Just equal, the two numbers.
Ah, so it's the genus of the
The genus, sorry, it's a little bit quick. The genus of these fibers is the same as this, because the canonical class goes to the plus minus the canonical class, and the fiber goes to the fiber, and so the intersection product is the same. Without Seiberg-Witten,
No, how can it be? Okay, we'll discuss.
no, I mean, if I were able to write the monodromic group in some way,
There is this notion of harmonic algorithm, which is invariant of Riemann structure, and it is deformation.
yeah, but you see,
Even
the
before one
Riemannian
remembers
structure
the
is
Riemann.
more than differentiable structure.
Okay,
Okay?
let's discuss.
You see, I'm just saying, before I just need homotopical equivalence. Here,
Yeah, but if you fix a differential structure, then the remaining structures are connected because they are convex.
what's the point? Yeah. But, I mean, you mean, yeah, okay, you can prove it without Sager-Witten, but with the same hypothesis.
Just using harmonic algorithm.
Okay. Yeah, sure. Okay, I agree. But anyhow, I need okay, the reason why I was not agreeing, I cannot make this hypothesis weaker, okay? Okay, very good. And now I use the Zoitensäge is that the number of mu is the number of singular fibers counted with multiplicity, and then mu is equal to the Euler number minus 4 times b minus 1, g minus 1. Okay? This is a classical formula, and observe that mu is the sum of mu t for tb, and this is 1 if and only if you have a node. Now, the conclusion is, now, mu prime is equal to mu. On the other hand, so this shows that the number is the same and each node remains. And the fact, so this implies that you get mu prime nodes. Here I need the deformation because they could otherwise they could just go together. But for a small deformation, for each small deformation. For small deformation, they remain distinct, these points. You get the family, the number is the same. And now, disconnecting, this means simply that the local monodromy here is a dentrist over something which is a product of commutators. Okay? And is detected by local monodromy. And by a small deformation, the local monodromy remains the same. So you see that whenever I get this situation, again, I get something. Now, there are these BCD surfaces. Okay, before I maybe pass to that, why is this interesting? So now, before I pass to the example, sorry, I wrote something. Now, why is this interesting? Because the Jacobians of the fibers here, they are of compact type. They are the product of these two Jacobians. So now I get B goes to the modularized stack of curves of compact type, and this maps to AG, the modularized stack of abelian varieties. So I get a complete curve. Now, deforming the curve is the same as deforming the surface. So now S rigid, B is rigid. And another question which I find quite interesting,
When you say B rigid.
B rigid is in M G.
Yes, but
And is B also rigid in AG? So this is some, interesting question. It has to do with the second fundamental quarter of the Toledo locus. So I'm not saying this is a difficult question. It just came up while finishing to write the paper.
Isn't it just directly?
Pardon?
Isn't it just directly?
No,
No, because
no.
you see,
He wants
the curve lies on a subvariety, and inside the subvariety cannot move, but it could move outside.
Yeah, so then the Jacobian,
This is
this
an embedding. We are, yeah. In some examples which we have, we have examples for genus 4. Then, of course, this is locally isomorphic. But for higher genus, it's not clear. Okay, so this is... now, I say that this is a curve. This is slightly imprecise, because if the number mu, see, if mu is different from 0, then they are moving, because this is irreducible and this is a product. So if mu is different 0, or mu equals 0 and not all fibers isomorphic, and Kodaira surface. So if mu equals 0, you must put the assumption that not all fibers are isomorphic, which is the definition of the Kodaira fibrations. Kodaira fibrations are really strong in the region. Okay, so is there an example of this situation? So now the example here, there is several examples, but let me explain the PCD surfaces. So now I take the following. I take P1 times P1. I will explain why I take this. And I take 3 horizontal, 3 vertical lines and a diagonal, okay? So you all know that blowing up P1 times P1 in these 3 points is the same as blowing P2 in this point. Now the advantage of this is that you see the vibration here. So I just take the curve here P1 with coordinates x, and then I define B to be the curve where I take the nth root of x0, x1 times x1 minus x0 to the power n minus 2. Sorry, this equation here defines B.
And what is x0 and x1?
X0 is 1 are the coordinates here on P1.
Not the homogeneous.
They are homogeneous coordinates.
On one.
Yeah, they are the coordinates on the base. Then I get some surface y.
And you assume that the points are 0, infinity, and 1.
Exactly, yes. 0, 1, and infinity. And I do the same here on all fibers. So this is really comes from hypergeometric integrals. I take the nth root ramified on 4 points. 3 are normalized infinity 0, 1, and the other is moving. So here I take z to the n equal y0 times y1 times y1 minus y0 times y1 x0 minus x1 y0 to the n minus 3 times x0 to the 3. So, okay, so I like equations, so you were asking, this is a very simple equation. I take here this 2, so I get this is a z mod n squared covering. And then I take S is the minimal resolution. But S is a covering of the del pezzo surface sigma. So what happens is that when you take the tensor surface, this is a P1 bundle, but you get a conic bundle because you blow up here, you blow up here, you blow up here. So you get these three fibers. Now you see that for a general fiber, you take a covering with this group of this fiber here. And essentially you get three fibers with one node, which is disconnected. Now the idea is that, well, this is rigid because it's on 3 points on P1. So that's why we started to conjecture the rigidity. Now, why is this interesting? This shows that for all deformations, these fibers remain. Okay? Now, this is a fiber. If it has two components, here, this fiber is like F prime plus F double prime. The self-intersection of this is negative. So I can contract this. So the theorem shows that the deformations of S, they correspond to equisingular deformation of what? Why is this singular covering? You see, over, I take 2 and root, so here when it's normal crossing is smooth, but over these points here, you get singularities. Now, and these are obtained contracting here, these curves. So,
On your picture, these curves are -1 curves.
no. Yes.
But they have positive genomes.
Yes, but you contract one of the.
I contract one of them.
One of them and each
Yeah,
one
yeah.
of these.
Yes.
Okay, and which one?
And you contract
Any or?
1/2 of each singular fiber.
But any or, you know, how you should. You can contract one.
Yeah, up to symmetry doesn't make it.
Doesn't matter, so.
Doesn't
Yeah,
matter.
it's-
Doesn't matter
okay,
because of
because of the symmetry.
So this shows that essentially, so I took an elementary case to show that here I have an argument proving that the deformation of the solution is the corresponds to the equisingular deformations of Y. Now, a little bit quicker. This is not the page. I want to show that something similar can be expected for other arrangements. So now I want to do the same for H, K, C, and for C, rigid arrangement. So this is somehow what I'm trying to tell you is the story of a failure, because I was trying to see, I mean, we asked these questions because I would have liked to find direct proof. So what is the difficulty? So let me give you a definition. What is a generalized hyperelliptic Fermat curve? C N N, this is the generalized Fermat curve. This means that C has a mapping to P1 with group Z mod N to the M minus 1 and branch on endpoints.
Okay. But there are many. There are many.
There are many. The difference is that for M equals 3, you get the Fermat, which is rigid, and this they move. Okay? So now assume that I have here a configuration, and I have a point P in the configuration such that the valency and the valency of P, the number of lines of the configurations, is at least 3. Okay? Now, to get S, I have to blow up P. So S has a mapping which I will call FP to one of these. So S is the, here's a good comment. Whenever I take the nth root of these linear forms, I get projection from here to P1, where I take the nth root of each of these. So I get a mapping to this. And this has genus at least 2 for m, at least 4 for m equal 3 and at least 4. Okay? So you see that some trivial inequalities come by the condition that this has genus at least 1. Now, I use again the topology that this has genus at least 2, so by the isotropic subspace theorem, or any theorem by CU and others, any S prime homotopically equivalent to S has a map, a similar map. So the idea is that if I deform S to S prime, in particular its homotopical equivalent, by topology, I continue to have this map here. So in a sense, S prime also has maybe an embedding in the product of this CP. Okay? Now, the delicate argument, so that one of the strategies to attack the general problem, okay, is to repeat this argument. Here, I was able to show that the fibers remain of the same type. Then I can contract. So here is the step which did not work. So if structure of the fibers is the same, then I can prove that the deformations of S are the same as the equisingular deformation of X, where X is the singular cover of P2. So there are 2 steps in the strategy, so the main point is to prove that. And now, this is not easy, but another question which I hope we shall soon attack. If C is rigid and N is big enough, then the episingular deformation of X is just trivial. So in a sense, what I'm suggesting here is to split the general problem in 2 parts. The first one, to show that the deformations are the singular deformations, and these are the one. I should say that in this case, we were thinking whether to write the calculation for this episingular deformation here, but it would have been another 10 pages. So I mean, it still is not completely easy. Okay, so this is concerning our questions of rigidity. Now, the next thing which I want to discuss is projective classified space. aren't visible. Looks like you can open them, but not.
Yeah, they are fixed.
No problem. Okay, so now I see that. Now, what do we know about projective classifying spaces? So, these, what are this class is stable, so X and Y are projective classifying space, then also X times Y. Because the fundamental group of these is the direct product. So this is like rigid, so to say, manifolds. Also their product is rigid apart from some exceptions. And what is important is that if X prime is isogenous's to X, which is a projective classifying space, this implies that X prime is a projective classifying space. Isogenous is the equivalence relation generated by finite unramified couplings. So, and maybe the main thing which I want to discuss is, and the action on the absolute Galois group. Okay, so projective classifying space contains curves, abelian varieties, and the locally symmetric varieties. What does it mean? This means that X tilde, the universal covering, is a bounded symmetric domain. And okay, what am I forgetting? Then there are, of course, Kodaira surfaces, Kodaira vibrations, and these Mosto-Zero surfaces, and in general, curvature, negative curvature surfaces are projective classifying space. Okay, so now what is the interest here is, what I find very interesting is assume that sigma is an automorphism of the complex number. So you see that the definition of projective classifying spaces is topological. And the whole modular theory somehow can be done algebraically or topologically, fixing the differentiable structure. So the main question does there exist X, a projective classifying space, such that the conjugate, so, is not a projective classifying space. So, the conjugate, sigma, means that you take the defining equations of X and you apply the automorphism, sigma, to the coefficients. Now, you might think this is a completely silly question, but it's an interesting question because up to now, we only know, if you look at all these examples, they are such that if X
This is Cardan theorem.
pardon?
This is Cardan theorem. Galois.
I'm going to say, exactly. I mean, everything started from the Cardan theorem. In fact, the Cardan theorem is a little bit weaker. It just says that if X is a locally symmetric manifold, then also X sigma is a locally symmetric manifold. And in fact, in my work with the scala, we prove that then the universal covering of X tilde is bioholomorphic to the universal covering of X sigma. And this is simply, I mean, this is by using Yao theorem, Kähler-Einstein metric, and certain holomorphic tensor. Okay? So we just made a very small addition, but this is somehow interesting because when you ask a question, you can always make it a little bit sharper, then it becomes false. So this is what I would like to describe now. And now, you see, I use this notation to make the theorem, the question correct. I say X is a projective classified space, and then now, if I would have been writing, if I write that X is K pi 1, does this imply that X sigma is a K pi 1? Exactly. With the same, this is no. And this is due, well, this is due to our theorem, which I proved with Ingrid and Fritz Grunewald. And there are surfaces for each automorphism sigma of in the absolute Gamma group that exist as isogenous to a product of curves such that the fundamental group of S sigma is not isomorphic to the fundamental group of S, which is phi. Okay, so this already was discovered many years ago by Serre, that there are conjugated varieties with non-isomorphic fundamental group, but here our example is a K pi 1, and here we proved it for each sigma not conjugated to complex conjugation, where it's true, and then the rest was done by Chaikin, Sapirain, and Gavino Gonzalez. So, first of all, okay, the group is changing, but it still could remain a projective classified space. Now, you can ask the question. Here, S is isogenous to a product of curve, so this implies that S tilde is the product of two half planes. So the universal covering is the same. Now, can we ask that the universal covering is the same? Now, this is no big theorem. I wrote it in this, the text of my lectures, but it's due to a theorem of Chabat. Says that there exists a non-rigid Kodaira vibrations as is such that there exists S prime, the formation of S, such that the universal covering of S is not isomorphic to the universal covering of S prime. No, isomorphic. Okay, so this is really, it's a very simple application of the result of Chabat. says the following. S tilde idea, at least I mentioned the Hero Shabbat, is that S tilde is omega, is some domain in C2 with small little regularity in the boundary, and the fundamental group of S in the automorphism, the bihomomorphic group of omega is finite index.
So there is no chance.
So there is only a finite number of choices, but if the codiera is not rigid. So you see that if you ask too much, you remain there. Still, this is very interesting, in my opinion.
Which Shabbat is the second?
So now the last part of my talk, because we still have 5 minutes. So this I cannot turn. So as I said, yeah. Together with, so there was a beautiful result by Inoue, which Inoue type varieties. So he worked for many years, and when he was at Max Planck, to construct certain surfaces. And these what we realized, this is also with Ingrid, and then there is some new work with Yongnam Lee. So what is an Inoue type variety? So it's rather long, but somehow it's related to the previous lecture because there was this thing about strong rigidity. And now many projective classifying spaces are strongly rigid. There are results of Id, Sampson, Seo, and many others. Okay, so I define X is an Inoue type variety. This is equivalent that X is a free quotient by a finite group of X hat contained in Z, which is a projective classifying space. So at least the definition, I like short definitions. Typical example could be like an abelian variety, and you have some group acting freely. In this case, they are Banera de Frankis varieties, so to say, and then you take an invariant
So
surface.
what is Z?
You're right. This is hypersurface entity. So X hat is in hypersurface and ample. Hypersurface is in Z. And Z is a projective classified space. Example. I take just X contained in an abelian variety. And X ample, okay? I mean, just to make it simple, I can just throw away the group. The abelian variety is a projective classified space. The classified map to the abelian variety is the Albanese map. So this is, I mean, you can generalize, but this is already the thing. Now, we have this, some results saying that if something is homotopically equivalent to Inoue type, it is again of Inoue type. But the result is very limited. And is limited treated for the following way, because if the degree of x is low, so if you have something which is homotopically equivalent to this, it will have the Albanese map here, but I want to prove that this is an embedding. Now, if the class is indivisible, then it's okay. So now the next question is, take a hypersurface here. And so the question, which I've been treating with Yongnam Lee, is the following. Deformation to hypersurface embedding. So I have like Z over T, and I have some W, sorry, over T. So I have a family, and this is a curve, and I assume that for t different from 0, psi t from W t to zt is an hypersurface embedding. So this is, I don't write all the hypotheses, this is all the fibers are smooth here, all the fibers are smooth here. There is some ampleness of the canonical divisor if you wish, but then the question, what happens for t equals 0? The particular case of homotopical equivalence is a deformation. So how can somehow a hypersurface embedding degenerate to a non-embedding? And here we have the following somehow example. So if you want, what I'm going to write here is, if you already have seen, you know, curves of genus 3. A curve of genus 3 is a quartic, and when it becomes hyperelliptic, it becomes a double covering of a conic. Okay? So this is the example which I'm reproducing. So an example, so we say, is standard. If I take something like TW equals sigma of Z, and then I take like W to the M plus W M minus 1 A 1. So you just take this variable here. So what I do here, I take a line bundle over Z. So W is, there is a line bundle over Z. W is contained here and is given by a pseudo polynomial in the bundle fiber variable, and then there is this equation here. Now you see that when t is different from 0, I can write W is sigma over t. So for t different from 0, I can write that W is sigma over t, and then I can eliminate. So, and then I get an embedding. But for t equals 0, I have sigma equals 0, and then I get the covering of degree n of some smooth hypersurface. So this is, like I said, think of this conic, and then the hyperelliptic curve of genus 3 is just obtained by taking here something of degree 4, intersects the conic in 8 points, and the double covering of the conic ranged in these 8 points is the hyperelliptic curve, which is the limit of vortex, where you eliminate this variable here. Now, okay, sorry, just one word. In general, you can iterate this. And what I think we've proven, but let me put like 9, I mean, we have still to write all the dates. Say like 90%, but I mean, this works, is that it is always so for m prime, it is standard. So for m prime, we can prove that every deformation to hypersurface embedding is obtained in this way. And the big question about which we are not sure is what happens for higher degree. Okay, thank you.
Fabrizio, I have a stupid question. You know, if you take x, which is locally rigid, then symmetric power, blow up, just take S2 and blow up, just symmetric power.
Yeah,
and
this
blow up diagonal, then it's also rigid. Because you know, your canonical contraction.
Yeah, but that's a very good point. In fact, I mean, this was proven by Barbara from Turkey. I mean, when she was a PhD student, this is what she proved. To get the surface, the deformation of the Hilbert scheme is the same of the deformation.
Yes.
But our question was for surfaces. Because in dimension 3,
Yes.
in dimension 3 you have rigid, something rigid, not of general type or whatever you want, which is not a classified space. So it's a very good point, but it's really superficial.
No, it's dimensional. So you are about dimension. Okay.
Yeah, we are about the dimension, but that's a good idea.
More questions, comments? Thank you very much.
Let me remind that tomorrow we have lectures in a different room. It is on the same floor, but it is room 108. A bit further.
Because I know my experience that wishful thinking